What do robust time series learning, geometric theories of nuisance, resistance, and a trillion-minute wearable health foundation model have in common? In this episode, we dive into 3 cutting-edge AI papers that are reshaping how machines learn from sequences, withstand real-world variation, and understand human health at scale. From contrastive learning without augmentation, to a unified theory of robustness, to a powerful foundation model for wearable data, these ideas point toward AI systems that are faster, smarter, and more trustworthy than ever. Let's explore the first paper, Divide and Contrast Learning Robust Temporal Features Without Augmentation. This divide and contrast learning, or DICOT, is an unsupervised time series representation method that removes 2 major costs in prior self-supervised learning: data augmentation and multiple encoder passes. Instead of contrasting individual timestamps, DICOT stochastically partitions each window into 2 to 10 overlapping subblocks, encodes them with a shared inception time backbone, and treats each subblock's immediate predecessor as the positive in a temperature-scaled cross-entropy objective. This reformulation makes the loss independent of sequence length and reduces similarity computation from timestep-level quadratic scaling to an OBK 2D objective, where k is far smaller than t. The design directly addresses false positives caused by assuming every neighboring timestep is semantically similar, a failure mode that hurts methods such as CAT on heterogeneous benchmarks. Across 6 large real-world datasets, including PAMAP2, WISDM2, HEARTH, ECG, SLEEP, and SCODA, DICOT reaches 83.07% average linear probe accuracy versus 81.2% for CATT and 80.69% for TNC, while training in 2.88 hours, faster than CATT's 3.47 hours and TNC's 11.48 hours. On 1% label data, it improves average accuracy to 76.36%, beating the best supervised baseline at 70.39% and TFC at 73.55%. It also leads on 124 UCR and 28 UEA datasets, with 81.33% and 71.24% average accuracy respectively, and tops clustering with 0.508 NMI and 0.406 ARI. The key novelty is temporal contrast as subblock classification, dense supervision, no augmentation bias, and multi-scale robustness from stochastic overlap. Let's explore the second paper, The Matching Principle, a Geometric Theory of Loss Functions for Nuisance Robust Representation Learning. This paper reframes nuisance robust representation learning as estimation of a single population covariance, STASC equals cov QNN, where n denotes label-preserving deployment variation, such as domain shift, photometric corruption, occlusion, temporal drift, adversarial perturbation, or style change. The proposed matching principle says the encoder Jacobian should be regularized along a PSD matrix S whose range covers range STASC. In the linear Gaussian model, this is both sufficient and necessary for driving deployment drift to 0, and when the range is matched but allocation is imperfect, the optimal trace budget follows cube root water filling. The paper unifies Coral, PGD adversarial training, augmentation, IRM style constraints, Jacobian penalties, and metric learning as different estimators of the same object, then makes the theory falsifiable with controls. Random, wrong W projections should behave like isotropic PMH, while signal-aligned penalties should hurt. Across 13 pre-registered blocks spanning MNIST, ImageNet-C, Coco Pose, NYU Depth V2, DomainNet, Cityscapes, QM9, Big Clone Bench, Whisper Small, UCI HAR, and Quintui, Coma, Pfeifmin, Zeven B, the matched arm passes 12 of 13 blocks. Examples include plus 4.3 percentage points on ImageNet-C, plus 22.4 pp PCK at 0.05 on Coco Pose, plus 11.1 pp rare class MIOU on Cityscapes, a 65% TDI reduction and WER drop from 23.26% to 14.63% on Whisper, and style.pmh preserving style TDI on Quen2 57B, while reducing sycophancy from 38.5% to 13.5%. The main failure, Office 3.1, is predicted in advance as an eigengap breakdown. Let's explore the third paper, Towards a General Intelligence and Interface for Wearable Health Data. This paper introduces Sensor-FM, a wearable health foundation model pre-trained with a masked autoencoder objective on more than 1 trillion minutes of unlabeled sensor data from 5 million participants spanning 5 modalities: PPG-derived heart rate and HRV, accelerometry, electrodermal activity, skin temperature, altitude, and sleep signals. Scaling both data and model size from 100K to 100M parameters produced near-linear gains, including a 31% lower reconstruction loss at the largest scale, a 74.8% reduction in random imputation MSE, and downstream gains of delta AUC equals 0.09 on classification and del TAR equals 0.21 on regression. On 35 person-level clinical tasks across cardiovascular, metabolic, mental health, sleep, lifestyle, and demographic endpoints, a frozen sensor FM encoder with simple linear probes outperformed engineered feature baselines on 34 of 35 tasks and achieved the best score on 31 of 35, with larger models also reducing dependence on demographic priors. The model's generative capability enabled high-fidelity recovery of missing wearables. After ablating 60 contiguous minutes, it preserved 99.7% step count accuracy, 99.9% deep sleep accuracy, and 99.2% light exercise accuracy in daily summaries. The authors then used a Gemini-based classroom of LLM agents to autonomously search downstream heads, running over 30,516 experiments, and improving performance on 29 of 35 tasks versus linear probing. Finally, integrating Sensor FM into a personal health agent improved clinician-rated context, personalization, relevance, justifiability, and harm scores across 1,860 blinded ratings with no significant difference, versus using ground truth labels, showing that model-derived predictions can ground safer, more useful health dialogues. That's a wrap on today's AI paper highlights. Thanks for watching.